Swayam Prabha. Digital India. Educated India.
Welcome you to this lecture module of flow through porous media. We were discussing about immiscible flow, and to be specific, we were talking about Barclay-Leverett front and movement of Barclay-Leverett front. We have already discussed about relative permeability and two-phase flow, and we are extending this discussion to Barclay-Leverett formulation. So, what we ended up in the last lecture was that this f w prime is equal to 1 minus f w. So, this is one expression that we ended up in the last lecture. What was the origin of this? If we go quickly to this, we had earlier we were talking about the oil produced, and then this expression we had integrated by parts. So, as I mentioned in earlier section, if you write u v dx, this integration is equal to u integral v dx, that is the first term here, and minus integration of u prime, that is derivative. So, that is why we have minus of dfw and integration of v dx, this entire thing again integrated over dx. So, this was the equation for by parts that I mentioned in the last lecture, and this is something which we had done here. So, we arrived at the Rp is equal to this quantity, where this SW represents the saturation at the outlet. And next what we did is we had talked about this Rp is equal to SW bar minus SWI, and so here we had now equating these two, we ended up with this expression that Fw prime is equal to 1 minus Fw by SW bar minus SW, and mind it, SW bar is the average saturation over the entire pore and SW is the saturation at the outlet. This is something we have in mind, because for writing this equation, writing this part of the equation, we have assumed that Vp is equal to 1 by Fw prime, or Fw prime is 1 by Vp. So, this is only valid if we measure this Fw prime, we estimate this. How do you estimate Fw prime? From Fw SW curve. So, we can draw a tangent. So, this must be done, this Fw prime must be done at a particular SW value, and that SW value corresponds to the saturation at the outlet, not any other SW value. So, then only this equation is valid. So, this SW is not any arbitrary SW, it is SW at the outlet. So, this is something which we got. So, now if we note further that DFW DSW, this is that slope of FW SW curve at a particular SW, that is equal to 1 by Vp, that is Fw prime is 1 by Vp, when we had written x equal to L Fw prime Vp, and then instead of x we put x equal to L, and this L was cancelled. So, that means we are talking about, so when we defined x equal to L Fw prime Vp, Fw prime is estimated at that saturation, and we are looking at displacement of that saturation from the inlet end. So, now we are saying we are forcing that x equal to L, that means displacement of that saturation packet is all the way to the outlet. Okay. And so, the situation that we are trying to simulate there, this F w prime corresponds to then the saturation at the outlet, because the same saturation for which F w prime is calculated, we are talking about movement of that saturation packet, and that displacement is x. So, that is why, so when we write dFw dsw, or in other words F w prime, so when we write F w prime is equal to 1 by V p, we are talking about this the case where dFw dsw is measured at some value of saturation that exists at the front when Buckley-Leverett front breaks through. So, that is something which we are making here, which we are assuming here. And this Vp is what? Vp is the cumulative water injected, and that is equal to till this point. That means, when Buckley-Leverett front has reached the outlet, till this time what was produced? Only oil. Okay. And what would be that value at that time? So, we are talking about the situation, just think of it, I am talking about a situation when Buckley-Leverett front has reached the outlet. Okay. Earlier case was somewhere in between, and then there was a drop to SWI and continuing, but at this time Buckley-Leverett front has reached the outlet. And so, at this time, till this point, this thing was linear, the cumulative oil produced versus water injected, that is linear. So, whatever water was injected, that same amount of oil would be produced, and that would be what? SW bar minus SWI till this point. Beyond this point, this will change. Beyond this point, Vp would be greater than SW bar minus SWI, because SW bar minus SWI represents the amount of oil that is pushed out of the system. SW bar is the average saturation, SWI is the initial water saturation. So, this difference arose because some oil I have pushed out of the system. So, this difference is the total oil produced, and since we are talking about the end point of this linear regime, so we can assume till this point the amount of water injected is equal to oil produced. So, that is why Vp is equal to SW bar minus SWI, and instead of 1 I can write it, I can extend it to 1 minus 0. I can extend it to 1 minus 0. So, 1 minus 0 divided by SW bar minus SWI. This can be written for dFw dsw at the SW that exists here. So, at this value of SW, this should be true. On the other hand, dFw dsw, if we look at just the previous slide, we have already shown that dFw dsw is equal to 1 minus Fw by SW bar minus SW. This is just in the previous slide we showed that this is true. Okay. So, now you think of the curve Fw versus SW, and this is again valid at that SW that exists, at the front. Now, you think of this curve, this was the curve, right. So, we are saying that we are looking at some kind of some SW value for the front, and I am saying on one hand these SW, say let us say I am talking about an arbitrary point, I say let us say this is SW. Okay. So, this is that SW at the front. So, I am drawing a slope here. So, we are saying on one hand this slope is equal to 1 minus 0 by SW bar minus SWI, and on the other hand the same slope would be 1 minus Fw by SW bar minus SW. Okay. And to separate things out, let us say I put another subscript 1 minus FWF, because this FW is calculated at this value of SW. Del FW, del SW is calculated at this value of SW. So, instead of calling it SW that exists at the front, let us write it as SWF and let us call this FWF. Okay. So, this slope has to satisfy these two conditions simultaneously. And how you can satisfy these two conditions? Now, let us look at the limits here. FW, the limit here is between 0 to 1, okay, and SW, we have some limit of SWI and further on that side. So, suppose I propose something here that SWF is that point which is, if I draw from SWI a tangent to this curve, if I draw a tangent to this curve which is this tangent. So, if I draw a tangent to this curve, wherever it, I mean if we try to draw from SWI, wherever it hits the curve, that point is SW, this corresponds to SWF and this corresponds to FWF. I mean I can say anything, where is the proof to it? So, let us see the slope of this line. The slope of this line is, and further if I say another step ahead and say wherever it cuts this line of FW is equal to 1.0, that means this line, wherever it cuts this line, I call this the corresponding saturation as SW bar. I mean I can say anything, but where is the proof to it? First of all, what is the slope of this line? Slope of this line is, here the FWF is 1. So, the coordinate of this point is x value is SW bar, I said, that is my proposition, and 1.0 y, right. So, this is the point, and this is the point I said x value is SWF, the front saturation, again that is a proposition, and the corresponding value of FW, this is FWF. What is the slope of this line? It is this y value minus this y value divided by this x value minus this x value. So, what is the y value? Y value is 1, here the y value is FWF, right. So, 1 minus FWF, I can see it is 1 minus FWF, and SW bar minus SWF, SW bar minus SWF. So, this particular slope is same as this. And if I look at the overall slope, that would be how much? The overall slope would be 1 minus 0. I know here FW is equal to 0. FW starts from 0 at SW equal to SWI, and FW is equal to 1 here when SW is equal to 1 minus SOR. So, here it is, if I look at the slope of this entire line, it is 1 minus 0, the change delta y is 1 minus 0 and delta x is SW bar minus SWI. So, slope of this entire line, if I look at the slope of this entire line is 1 minus 0 divided by SW bar minus SWI, and that is exactly this one. So, I can see that from SWI, if I draw a line which is tangent to this curve, so wherever it hits the curve as tangent, that point is SWF, correspondingly we have FWF, and wherever, if we extend this tangent, wherever it hits the FW is equal to 1.0 line, that is going to be the SW bar. Then that fits perfectly to this definition, because both these FW prime values I have to satisfy, and this is only possible if we call this SWF and further extend, and wherever it hits we call that as SW bar. So, this is going to be a very crucial figure altogether, right, because suppose I give you the expression for KRO and KRW, or KR waiting phase and KR non waiting phase. So, I have to give you some form of equation, say let us say KRW is equal to some correlation I have to give in terms of SW, and similarly KR non-weighting I have to give you some as a function of SW. See, once SW is since we are talking about two phase flow, if SW is defined, automatically the other saturation is defined. It will be simply 1 minus that quantity. So, let us say I give you these expressions. If you have these expressions, immediately you can calculate what is FW as a function of SW. So, you can construct this curve. Moment you can construct this curve and locate this SWI, you can simply draw a tangent to this curve. You do not have to do anything, just locate these points using this expression, you get these points, fit a line through them, and then simply draw a tangent from SWI, and wherever it cuts we call this SW bar. So, now the problem is resolved. At what point this will happen? It will happen, what is the corresponding RP? RP is simply SW bar minus SWI. SWI, I have already, I know the system, the porous medium, it may be having say 0.1 is SWI is 0.1 or SW is 0.2. So, that the porous medium, that any experiment on that porous medium, the experiment that we mentioned, initially it was all water and then we inject oil for 10 to 24 volumes, see what is the end point saturation, then we inject again, instead of oil we inject water again and 10 to 24 volumes, see what is the end point saturation. So, there I mean SWI can be done separately from the experiment, that would be provided, and SW bar already I have drawn the curve. From SWI I will draw a tangent wherever it hits the FW equal to 1.0 line. So, that is SW bar. So, moment I have SW bar, moment and SWI I already have, I subtract these two, that would be the oil produced, the pore volume of oil produced till the breakthrough. I can immediately get that, nothing, no more calculation. So, this is the immediate calculation we can do. So, till this time there would be it would be 45-degree line, and beyond this time it will start turning, but this point we have already located. Okay. And what is this SWF? If we try to find out what is the saturation profile, so this SWF would be this point. I mean, we draw a tangent. So, when the Buckley-Leverett front breaks through, that means I started injecting water, and that water, here I am injecting pure water, no oil, I am pure water in the sense only water, not water plus oil. So, water is injected, and that means wetting phase is injected. So, here I can maximum I can go is 1 minus SOR. So, that is the maximum we can go 1 minus SOR, because minimum SOR amount of oil has to remain in the pore space, and in between there would be saturation will decrease slowly, and at this point this is just the time when the Buckley-Leverett front has broken through. So, this is the corresponding SWF we have. Now, suppose I want to know what is the at this distance, let us say at x equal to 0.75 L, that means 3/4 distance, 3/4 of the length. If we go 3/4 of the length from the inlet, what would be the corresponding SW? How will I find out? I need to construct this curve, right. So, to construct this curve, what we have to do is, first of all, I pick up another saturation. See, mind one thing, this particular saturation is the front saturation. So, we are talking about this part of the curve, which is important to me, because I can see beyond SWF, it is water saturation is increasing inside the pore. So, we do not need to bother about this lower part of the curve below SWF, we are concerned with the upper part of the curve. So, at any point I draw a tangent, here I can draw a tangent. So, any point you can draw a tangent, and that, so suppose I draw a tangent, I can find out immediately what is the corresponding FW prime. Okay. So, suppose I want to know this particular saturation, I mean suppose some other saturation here. What does this curve mean? This curve means I have this SWF saturation, and given this after Vp volume of water injection, this SWF saturation has travelled by distance x equal to L. I am talking about a higher saturation, a packet with higher saturation. So, that will also travel by some distance which is x, but not L. So, how far that saturation will travel? So, how do we get that? Now, we have to use this equation once again, x equal to L Fw prime Vp. That is that same mother equation one has to use. And in that same mother equation, we see Vp is already known because it is that curve that is frozen. This is after Vp pore volume of water injection. Now, I am just interested in the saturation at any intermediate location. So, the Vp is fixed. Vp is fixed. I am just for the same Vp, we are looking at different saturation packets, how far they have travelled. So, Vp is already fixed, L is fixed, and Fw prime. So, for corresponding saturations, I have to draw a tangent. So, for this saturation, I have to go up, draw a tangent, find out the slope, use that as the Fw prime, because that would be the governing Fw prime. And with that Fw prime, with the given Vp and L is known, how far that saturation front will travel. I find this will travel up to this much, this saturation packet will travel up to this much, this saturation packet will travel up to this much, right, like this. And the saturation packet which is having 1 minus SOR, which is near the end, okay, this will not travel any distance. So, because the x is equal to 0 in that case, that means Fw prime has to be infinity in that case. So, this is how this curve has to be read, and from this curve for drawing tangent at different locations. Now, drawing tangent in the sense that we are doing it graphically just to get a better feel for this. If somebody wants to do it analytically, that is also perfectly acceptable, because you can have an expression, analytical expression of Fw versus Fw, that fractional flow curve as a function of saturation, and that function can be simply differentiated. Okay. So, this is something which one needs to do for finding out these locations. And in fact, now when this thing exceeds, now suppose this you have reached the outlet, you have already found these curves. Now, when you go beyond this point, let us say when this front has travelled out from this, further water was injected. So, at that time the saturation front will take the shape something like this. So, here the SW will be higher. Now, this would be the SW, but this SW would be higher, not SWF. SWF is unique for this system, and that is when Barclay-Leverett front has reached the outlet. But now, if you have another SW, so you go to that SW, find out what is the Fw prime for that SW. Okay. So, with that Fw, you can find out then Vp is equal to, for when SW is that same that at the outlet, then one will have Vp is equal to 1 by Fw prime. So, now for that particular SW, we are looking at some other SW at a higher value of SW. This is the new SW, because some more injection has taken place. So, the Vp has changed. So, now we have to draw another tangent to this curve here, find out what is the corresponding Fw prime, take the reciprocal. So, that would be the Vp. Okay. So, for that Vp, so that would be the Vp of water injected, and then one has to find out then correspondingly these tangent wherever it hits this curve, that gives you the SW bar at that time. So, again you have to repeat that same exercise of SW bar minus SWI, and then one has to repeat that same exercise to find out the corresponding value of, once you get SW bar with SWI, you can get the corresponding RP, and then again you repeat these points for various saturations, how far it traveled. So, you can get this curve, and you can generate these points here. And once this, so if this, when this process continues, at the end we expect that this entire porous medium will have 1 minus SOR, that saturation. So, entire porous medium will be having single saturation. So, this is how this saturation will continuously grow to a single value of the saturation of 1 minus SOR, the end point saturation for this porous medium. And at that time you would say asymptotically this production cumulatively it is not changing anymore, it is the horizontal, this line. So, it is not changing anymore. So, these points you can track it down. I presume, I mean, you can track these down. One can very well take some value which is higher than this SW, draw a tangent at this place, find out the corresponding SW bar, find out this is the SW, against that this is the SW bar. So, find out the difference to find out what is the RP produced at that time. Okay. Against what is the VP? 1 by FW prime is the VP. So, against this VP how much is the RP produced. So, from there again with that VP, now you send several packets to this end, and then at that time your FW prime would be for all points higher than these. So, let us say this point, this point. So, this is the outlet saturation at that time. So, beyond this outlet saturation, whatever saturation values are there, so there this FW prime will be different, again the FW prime will be different, you have to put those corresponding FW prime. VP is same as 1 by FW prime corresponding to the outlet saturation that you have chosen to start with. So, that VP will remain there. FW prime is based on these new saturation values, you have to draw tangent and find out, and you can locate what would be, how far it would travel, how far a saturation packet will travel. So, you can generate this curve, and you can continue to generate these curves, and based on to start with, wherever you are, corresponding SW bar, that SW bar minus SWI will give you the, for that particular VP, which is 1 by FW prime for this SW. So, for that particular VP, how much of oil produced is given by the corresponding SW bar here minus SWI. So, that so you can get so you can generate these points as well. So, one can use one can perform this exercise to generate these curves. So, this is more of a graphical construction, and this construction would be made much easier if parallelly one draws, instead of FW SW curve, but the same SW, for the same SW, if somebody draws FW prime curve also. So, it starts from SWI, ends at SOR, and in between it goes like this and then comes out like this. So, this is FW prime goes like this. So, instead of drawing tangent at every point and then doing this calculation, instead of that, if first you pick up some points here and generate this FW prime curve, then it would be easier. I am talking about this saturation, we do not have to draw tangent to find out what is the slope. Directly we can read what is the corresponding FW prime. So, generally this is customary to draw FW prime curve also just against the same saturation, against I mean you draw the saturation axis so that they correspond to each other, so that you can simply vertically you can raise these lines and find out the corresponding FW prime curve. So, probably this becomes somewhat easier, and if somebody can solve this analytically, even they can generate this curve analytically also, then you do not have to draw tangent either. So, this is all I have as far as this particular lecture module is concerned, and I more or less discussed about this Buckley-Leverett method, and then I mean my next aim would be to conclude this Buckley-Leverett method and then extend this whole understanding. Now, if we are talking about oil and water. Now, instead of that, if we have a 3-phase system, and further moment we have 3-phase system, when oil and gas both are involved, then one may have to consider something called a PVT relationship between oil and gas, because some components from oil will go to the gas phase. That I mean oil and water, they are immiscible, but moment you bring in gas, you can never exclude that possibility. So, that also there, I mean how to address that, I will very briefly touch upon that in the next lecture. That is all I have as far as this module is concerned, this lecture module is concerned. Thank you very much.